There is a number burned into every AI system you have ever used, and almost nobody talks about it. That number is called a training cutoff date, and it means that every response you have ever received from ChatGPT, Claude, Gemini, or any large language model was generated by a system that is, at its core, frozen in time. Not metaphorically, literally. The model that answered your question today learned everything it knows from text that existed before a specific date, and after that date, it stopped learning entirely. The world kept moving. The model did not. Here is why this should genuinely concern you. Right now, as of mid-2026, the AI tools that hundreds of millions of people use daily for medical research, legal guidance, financial decisions, and hiring recommendations are operating on knowledge that in many cases is 18 months to 2 years out of date. IBM stock collapsed more than 25% in a single session this week after a dramatic earnings pre-announcement. If you asked a standard large language model about IBM's financial health before that news broke, it would have given you a confident, well-structured answer based on data that no longer reflects reality. That answer would not have been a hallucination. It would have been worse, because it would have been accurate for a world that no longer exists. The Federal Reserve has a new chairman. Drug approvals have changed. Supreme Court precedents have shifted. And the AI guiding your decisions knows none of it. To understand how we got here, you need to understand what training a large language model actually involves. Starting around 2018 with GPT-2, then accelerating dramatically with GPT-3 in 2020, companies began scraping enormous portions of the internet, books, academic papers, and code repositories, then feeding that text to neural networks as a single, massive, static dataset. The process of training a frontier model like GPT-4 took months and cost, by credible estimates, over $100 million. You do not retrain a system that expensive every week. You train it once, freeze the weights, and deploy it. Think of it like printing an encyclopedia. The moment it goes to press, it is already slightly out of date. The difference is that an encyclopedia never claims to know what happened yesterday. An AI will answer confidently regardless. This architecture was a practical necessity when these systems were first built. It has since become one of the most consequential design decisions in the history of software, and most users have no idea it exists. The first thing most people do not realize is just how severe the confidence problem is. When a language model does not know something because the event happened after its training cutoff, it does not say it does not know. It constructs an answer from patterns that feel adjacent to the truth, and it delivers that answer in the same measured, authoritative tone it uses when it actually does know. Researchers at Stanford and MIT ran systematic evaluations in 2024 and 2025 showing that models confidently produce false or outdated information at rates exceeding 30% when queries touch on events near or after their knowledge boundary. 30%. That is not an edge case. If a bridge had a 30% failure rate under certain conditions, you would not drive across it. But millions of people cross this bridge daily, for decisions far more consequential than trivia. A model trained before March 2025 does not know that the 2026 World Cup is currently underway, does not know the current playoff structure, does not know Holland's tournament statistics. It will still answer your question about it. And that gap between what it knows and what it says it knows is not a bug that can be patched. It is structural. Now here is the part that genuinely overturns what most people assume. You might think the solution is simple, just update the model more frequently. But the architecture of how these systems store knowledge makes that nearly impossible without starting over. Human memory is associative and continuous. You can learn that a friend got a new job and immediately update dozens of connected beliefs about their schedule, income, and availability. Large language models store knowledge in billions of numerical weights distributed across layers of a neural network, with no address book, no index, no lookup table. When you try to inject new facts into a trained model through a process called fine-tuning, a phenomenon called catastrophic forgetting kicks in. The model does not add the new information alongside the old. It overwrites it. In one well-documented 2023 experiment from DeepMind, fine-tuning a language model on new factual data caused it to lose up to 40% of its previously accurate responses on related topics. The new knowledge does not slot in. It displaces. This is why the leading labs do not continuously retrain their flagship models. It is not laziness or cost-cutting alone. The very structure that makes these systems so impressively capable at reasoning also makes them fundamentally resistant to being updated. The mechanism behind this comes down to how transformers, the architecture powering virtually every major AI model, encode information during training. When a transformer reads text, It adjusts billions of numerical parameters called weights through a process called backpropagation, essentially nudging numbers slightly each time it sees a pattern until the whole system settles into a configuration that predicts text well. Think of it like tuning thousands of radio dials simultaneously until a signal comes in clear. Once the tuning is done, every dial is set. The knowledge is not stored in one place, the way a database stores a fact in a row and a column. It is distributed fractally across the entire network. There is no single weight that stores the fact that a particular election happened or a drug was approved. The knowledge lives in the relationship between millions of weights simultaneously. This is precisely why these models can reason and generalize so powerfully. A concentrated, modular architecture could not do what they do. But it is also precisely why you cannot update one fact without risking the integrity of thousands of others. The capability and the flaw are the same thing. The industry is not sitting still on this problem, but the proposed solutions each carry their own serious complications. Retrieval-augmented generation, known as RAG, connects a model to a live search index so it can pull current information before generating a response. But RAG introduces a new failure mode. The model must now decide which retrieved documents to trust, and researchers have demonstrated that adversarial content, basically misinformation planted in index sources, can manipulate model outputs at scale. A 2025 paper from Carnegie Mellon showed that injecting false claims into just 45 websites was sufficient to corrupt responses from RAG-enabled models across multiple platforms. The second major approach, building AI agents that browse the web in real time, trades the static knowledge problem for a latency and reliability problem. These systems make errors when web pages are ambiguous, paywalled, or structured for human eyes rather than machine parsing. Neither fix addresses the root architectural tension. Both transfer the risk rather than eliminate it. This matters to you in ways that are already arriving, not theoretical. If you work in law, medicine, finance, journalism, or any domain where current information is not optional, you are already interacting with tools that your colleagues are trusting at levels the technology cannot yet support. The paralegal using AI to summarize case law needs to know that precedents from the last 18 months may be entirely absent. The financial analyst using AI to assess sector exposure needs to know that the model's picture of the sector is frozen. By 2028, regulatory pressure in the European Union under the AI Act will require explicit disclosure of training cutoff dates in high-risk applications. The United States has no equivalent requirement yet. Concretely, before you act on any AI-generated information, ask it directly what its